So my name is Chris Maclellan. I'm an assistant professor at Drexel University, and today I'm going to be talking about some preliminary work developing an approach that we're referring to as you got me mixed up, convolutional cobweb, not computational cobweb, which is an incremental model of learning from 2D images. So just to set the context for this, many cognitive system approaches often assume high-level symbolic representations are available for interfacing with the world. And to support learning from pixel-level representations or pixel-level inputs, they often utilize off-the-shelf or pre-trained object detectors and classification algorithms. So I took this system diagram for the Aline system that was presented at this conference last year. And you can see here that they have this vision module that's using YOLO to translate the images that are coming in from the world into labels that are then being processed by SOAR. Now, the most common approach that I've seen in the literature is to utilize a convolutional neural network model like YOLO or something like ResNet to translate from 2D images into higher level symbolic representations like labels of objects or things within the scene. So unfortunately, there are many limitations of this kind of CNN-based approach, and I'm just highlighting a couple of them here. First, training is a non-incremental. So these models are often trained offline and in batch, and then no learning happens when they're being used in the system. Additionally, the structure of these models is fixed at training time. So often when you're building one of these neural network models, you pick how many layers you want and how many nodes per layer, and that's fixed. It can't be adapted based on the input. So for example, you can't expand the number of nodes or expand the number of possible outputs at runtime. And they also often require a large amount of training data. Now, it's worth mentioning that there are some alternative approaches out there, such as the probabilistic programming work of Lake and Tenenbaum et al. But these approaches, they have some nice, interesting results that show that they're able to reduce the amount of training data by bringing in some prior knowledge into their models. But these models still use non-incremental training paradigms, and they often adopt fixed model structures where only the parameters are estimated. So to address these limitations, we've been exploring an approach that's based on prior concept formation models. Now, concept formation models are a type of model that emphasize the incremental nature of learning and the ability to adapt conceptual structures to better reflect their experience. And the basis for our approach is a model called Cobweb, which was developed by Douglas Fisher. And we're actually utilizing a variant of Cobweb referred to as Cobweb 3 that supports the ability to handle both discrete and continuous valued attributes. So for people here that aren't familiar with Cobweb, I'm just going to do like the crash course and give you just an intuition for how Cobweb works. So imagine that we have an instance coming in. In this case, we have something in the world. It's got a color and a shape. The color is red, the shape is square. And we have a cobweb tree on the right that's currently just empty. It just has an attribute value table in one of its nodes at the root. So when the instance comes in, we update the attribute value table to reflect the probability distribution over the features in that instance. So now we get a new instance. In this case, the color changes. Now it's green. So when the example comes in, we update the tree. We actually do a type of, we create like a new node that branches off of the root. So now we have the root summarizes all the examples that we've seen so far. And now we have two children, one that represents green squares and one that represents red squares. These are the concepts that are organized within our classification tree. So now we might get a new example. In this case, now we have a green circle. So we update the probability distribution at the root. And as we sort it down the tree, we continue to modify our tree structure to better represent the distribution of the examples that we've seen so far. So during learning and performance, I just showed this just a very quick example, but Cobweb during learning is using 4 different operations to update its nodes. It's adding the instance that it's incorporating into a node. It can create new nodes. It can merge existing nodes and then add the instance to those. And it can also split nodes and promote the children. And it chooses the operation that maximizes the category utility measure, which is developed by Corder and Gluck. And this measure is based on a study of human basic level concepts. So it's really they're trying to figure out how to, they quantified a way to represent concepts that are very predictive of the features that they contain. And you can ask me more about that. I can go into more detail. Now, at performance time, Cobweb only considers 2 operations. It considers adding and creating, and it doesn't update if the attribute value counts of the nodes within the tree. Now, and the final node that an instance is sorted into is then used to generate predictions about that instance. So we might predict, its color. Given just the color, we might try to predict the shape, or we might predict some type of label about those things based on the distribution of things we've seen before. So there are a couple of limitations of Cobweb for the kind of work that we're trying to do here. And one is that Cobweb and other concept formation approaches in general have historically also assumed a higher level representation. So usually they're talking about things like shapes and colors and not pixel level representations. And so, I've been thinking a lot about other approaches like CNNs that are handling this kind of data. And CNNs are leveraging convolutional processing to actually learn a representation of the input, which is then used to make decisions like classification decisions about the input. So our work aims to explore how convolutional processing could be incorporated into a Cobweb model to support incremental learning over images. So to support this, we developed a version of like an MNIST classification, which I'm calling the Incremental MNIST digit classification task. And we're using images like the one shown on the left, where we have handwritten digits and their labels. And what we do is we provide an image to the model without a label. We ask the model to make a prediction to predict what the label is. Once it generates a prediction, we can evaluate that, and then we provide the same image with the label for the model to incorporate into its memory to learn. And this process just repeats. It's kind of like a form of like temporal cross-validation. So first, I just want to talk a little bit about convolutional processing within a very simple one-layer CNN that's just using a single convolutional filter. So for people that aren't familiar with this, the way that this works is you have a 3x3 convolutional filter, and the CNN actually convolves this filter over the image in order to generate a set of outputs that are shown on the right. And once we've generated these outputs, then these outputs are passed often through some type of classification layers, could be multiple layers, could be one, and that is then used to produce an image label. Now, let me talk about what this looks like once we start to incorporate this idea of how CNNs are processing images with the Cobweb approach. So now we have our pixel level input on the left. In this case, I've just shown an image of a 3 sort of in the background. We have some convolutional filter hierarchy. It's actually represented as a Cobweb tree of filters. And then we have some type of intermediate representation. And as we're going to do the same thing, where we're going to convolve over the input like a 3x3 filter. And as we do that, we're going to update our hierarchy of convolutional filters. And as we move this along, you'll see that the intermediate representation we learn on the right is actually using the labels of the filter concepts that we're learning as our intermediate representation. And once we've done this, then we take this intermediate representation and we pass it through a higher level classification hierarchy, which is then used to identify a final concept that represents this input. And we use that concept in order to generate a prediction about the image. So one thing that's important to note about this is that we're learning both an intermediate representation, and we're using that intermediate representation to learn some concepts about the input. Another thing that's interesting in comparison to the CNN is that unlike the CNN, which has a fixed structure, our convolutional filter structure is it's adapting as it sees different kinds of inputs. So just as a very preliminary evaluation of this idea, we compared it to the 2 different sort of base models that we tried to combine together. So we compared it to a simple one-layer CNN, which in some sense is lacking this idea of incremental concept formation. And we also compared it to a Cobweb 3 model that's mapping from pixels to features directly. There's no intermediate convolutional filter processing. So what we found, so what we did is we took each model, we applied it to the incremental MNIST prediction task, and it was presented with 300 images, which was 30 images of each of the digits. The images were presented in a random order where each of the models for each run saw the same ordering, so that we tried to reduce the variation between the models. We averaged over 50 runs, and we find that our approach seems to outperform the 2 approaches that it was based on. And again, this is just very, very preliminary, just initial test of this idea to see if there was even any promise here. We also looked at some of the learning curves. So what we found is that both the Cobweb models seem to converge much more quickly. They have a much steeper learning rate at the beginning than the CNN. And this is because, and I'm glazing over a lot of the details here, the CNN model is doing stochastic gradient descent in batches. And it just takes a really long time. You need a lot of updates before the model starts to converge. Additionally, during training, our approach is only slightly better. This convolutional cobweb, it seems here, they're very like similar performance, Cobweb and Cobweb 3, but it is consistently performing better than the regular Cobweb overruns and across time. So just my conclusions in my future work, we claim that we've come up with a novel unification of convolutional processing ideas from computer vision research and classical ideas from concept formation literature. And we believe that our results show some initial promise, but a lot more experimentation is needed to better understand the behavior of our model. And I just want to say that I think that there is real potential in this kind of idea to generalize this sort of union of these two ideas to other kinds of concept formation approaches beyond Cobweb. So for example, SAGE might learn some representation of filters, use those filters and to learn some representation of concepts. And ultimately, we hope that this kind of research will lead to incremental learning modules that can serve as alternatives to things like CNNs within cognitive systems. So with that, I'll end there and take questions.